We've spent time in our last couple of videos looking at series which could be derived by taking the geometric series and modifying it in several ways, either by replacing x's with x squareds perhaps, or maybe taking an integral of the geometric series and the function that it equals on a certain interval. But today we'd like to explore series that can be obtained in other ways and which cannot be obtained by modifying the geometric series. I'd like to begin by asking you a kind of a silly question, and that is sine of x a polynomial? Or maybe better stated, is there a polynomial that might represent sine of x? In order to start exploring that question just a little bit, I'd like to take a look at several polynomials. You remember what polynomials look like, right? I mean, perhaps if I take 0.5 x to the, where are we here? Let's see, 0.5 x, let's say squared, plus 2x minus 8, something like that. And we'll zoom out a little bit here so we can see what that looks like. So that's a quadratic function, forms a parabola. The thing I want you to notice in particular is that whenever x is large, either in a negative way or in a positive way, that the values of f of x are small. The values of the quadratic are small. If I had used a negative coefficient in front of the x squared term, well, now we have exactly the opposite being true, right? Whenever x is large but negative, or large but positive, then the values of x become very large and negative, right? So that's one example of a polynomial. If I used a cubic, right, in this particular one, we have large x values whenever x is negative. We have large but negative x values whenever x is positive. And we're always going to have such behavior with polynomials. It doesn't really matter how many terms I've got, right? Doesn't matter how many terms I've got. A cubic is going to behave. It's going to have beginning and end behavior similar for coefficients that are negative. Also, we're going to have similarly behaved conditions whenever, or consequences whenever the coefficient of the highest degree term is positive. Anyway, we're always going to have large y values, either positive or negative, for large x values. However, right, the sine graph does not behave that way at all, right? The sine function oscillates, always goes between -1 and 1, never has large x values, either positive or negative. And so the answer is quite obvious, really. No, sine of x cannot be represented by any polynomial. However, let me take a very simple polynomial and compare it with sine of x. The polynomial of one term, just x, right? And notice that the graph of x is very, very close to the graph of sine of x, at least for values of x near 0, right? The graphs, in fact, are almost indistinguishable over this small little interval, right? And there are other polynomials that get even closer still. Let me take a look at this one. Whoops. There we go. So x minus 1/6 x cubed. Wow, that really hugs the graph of sine of x on the interval, looks like between -1 and 1, and even just a little bit further. let's try another one. Let's add on to that 1 over 120 times x to the 5th power. Wow. Here, between -1.5, maybe even a little further, and 1.5, we get a lot of similarity between the graph of the polynomial and the graph of sine x. You know, just look at a couple more. 1 over 5040 times x to the 7th. So we'll add that on there, and my goodness, we're between -3 and 3. The graphs are almost indistinguishable. I'm going to try one more here. Let's tack on 1 over, this is just crazy, 362,880. And let's see, you can probably guess what power I'm going to put on here. It started with power of 1, then 3, 5, 7. Here I'm going to tack on x to the 9th with this coefficient. And yeah, it looks like between -3.5 and 3.5. It's just remarkable how similar these graphs are to one another. Right. So while sine of x cannot be represented by a polynomial, at least not on the entire wide interval, the entire interval from -infinity to infinity, by any particular polynomial, if we restrict the domain on which we want these functions to agree, it looks like we can get really, really close. And going to the whiteboard here, it looks like, right? It looks like sine of x is, well, this is the polynomial that we just looked at. Between -3.5 and 3.5, these two functions agreed very, very closely. And so what I wish, so I know I can't do the job with a polynomial, but I wonder if I can do the job with a power series. And really a power series, this is an example of a power series. A power series can be thought of as an infinite polynomial, a polynomial with infinitely many terms. Now, by definition, a polynomial has only finitely many terms, right? So to talk about an infinite polynomial doesn't really make a lot of sense. But I can think of functions that are made up of power functions, infinitely many of them. Can't call it a polynomial, but I can call it a power series. Let's go back and look at this one more time. All right, so I kind of want to wish that there were a power series out there and one centered at 0, right? Remember what centering means. Centered at 0 means that if I put 0 in for x into the series, that the series collapses, right? Collapses down to a single term, and that's what happens here. If I put 0 in for x, this all collapses, the series collapses down to just 0, right? So 0 is the center. And so I'd like to see if I can find a power series centered at 0 that's actually equal to sine of x. So the first consequence of my wish is this, that sine of x is equal to, well, here's the most generic power function that I can write down. Right, I've written down a term for a constant. I've written down a term for a first degree function, a power 1, power 2, power 3, and so on. And the question is, what are these coefficients going to be? Well, there's actually an observation here that can get us started pretty quickly. And that's the one that notes that we're starting with a power series that's centered at 0. In other words, whenever x is 0, this all collapses down to just the term a sub 0. Fine. If this power series is going to be equal to sine of x, then that means that, well, whenever x is 0, well, if these are equal, whenever x is 0, I'm going to have an equality. So, but if x is 0, then the power series goes down to a sub 0, and the value of sine at 0 is simply 0, right? So whenever x is 0, this reads sine 0, which is 0, equals a sub 0 plus 0. So a sub 0 must be 0. So already I have my first term. My constant term is 0. And notice I had no constant term appearing in the polynomials that we were looking at earlier. Another observation is, well, let's see. If I have two functions that I'm claiming to be the same, well, then their derivatives are going to be equal as well, right? If this function's the same as that function, then the derivative of this function must be the derivative of this function. And so let's just write that down specifically. So derivative of the left side is cosine of x. Derivative of the right side is, let's see, derivative of a constant is 0. Derivative of a1x, well, that's just going to be a1. Derivative of a2x squared is going to be twice a sub 2 times x. Right? It's easy to find derivatives of these power functions. 3a sub 3 times x squared, 4a sub 4 times x cubed, 5a sub 5 times x to the fourth. I could do this all day. 6a sub 6 x to the fifth, right, and so on. But I won't do it all day. I'll stop there. We get the idea. But now I can play the same trick I played before, right? X, if x is 0, the right side collapses down to a1. Everything else goes away whenever x is 0. Whenever x is 0, over on the left-hand side, I have cosine of 0, which is equal to 1. Right? So this reads, whenever x is 0, this reads cosine of 0. So 1 equals a1. So we found the coefficient of x, which in fact agrees with the polynomials that we were looking at through the graphing program. I can continue this process. Derivative of cosine x is negative sine x. And the derivative of the right-hand side, well, again, derivative of a constant is 0. Derivative of a constant times x is that constant. Derivative of 3a sub 3x squared, that's equal to, well, that's equal to 6x times a3. Next one is, and I'm going to write this, and you're going to see why in a moment. Instead of writing 12a4, I'm going to write 3 times 4. a4 x squared. And I'm going to continue that process. 4 times 5, a5 x cubed, 5 times 6, a6 x to the fourth, and so on. Get the idea? Play the game again. If x is 0, everything over here collapses except, well, it collapses, and it collapses down to twice a2. Whenever x is 0, the left-hand side is 0. So that says that 0 equals twice a2. Well, that says that a2 must be 0 over 2. a2 is 0. Which again agrees with the polynomials that we were exploring before. I didn't show a x squared term because the coefficient's going to be 0. I don't need to write it down. Do it again. Derivative of negative sine x is negative cosine x. Derivative constant is 0. Derivative of, oh, what did I do there? This should have been, I guess I was okay. 6 times a3 times x, 6 times a3 times x. I wrote it a little funny, but that's going to be 6 a3 Derivative of this is going to be 2 times 3 times 4, a4x, 3 times 4 times 5, a5x squared, 4 times 5 times 6, a6 x cubed, and so on. Same trick. If x is 0, this side collapses to 6 times a3. Left side collapses to negative cosine of 0, negative 1. So this is negative 1 is 6a3. Well, divide both sides by 6, and I have that a3 is negative 1/6. Again, that agrees with the polynomials that I was looking at before. Do a couple more times. Derivative of negative cosine x is sine x. And can we see what's happening? Right, so the next term I'm going to write down, right, derivative constant is 0. Next term I'm going to write down is 2 times 3 times 4, a4. And then I'll have 2 times 3 times 4 times 5, a5x. I'll have 3 times 4 times 5 times 6, a6x squared, and so on. So I'll have, well, this is 4 factorial right here. 2 times 3 times 4 is 4 factorial. So what I have is 4 factorial times a4 is 0. So a4 must be 0 divided by 4 factorial. Well, 0 divided by any non-zero number is 0. So that tells me that a4 is 0. But look what's going to happen in the next step. In the next step, this guy is going to bubble down. Let's see. So my derivative is going to be cosine of x. But my new constant term is going to be 5 factorial. See that? 2 times 3 times 4 times. So 5 factorial times a5. Next, I'm going to have 6 factorial times a6 x, and so on. So whenever x is 0, this side collapses down to 5 factorial times a5. Cosine of 0 is 1. So a5 must be 1 divided by 5 factorial. And if you'll check, 5 factorial is in fact 120. And so that agrees with what I've got there as well. So I think we can see what's happening now. So every other time I'm going to have, let's see, I'm going to have either sign or negative sign appearing on the left. That's going to be 0. So whenever I evaluate, well, whenever I evaluated a sub 0, I got 0. Whenever I evaluated a sub 2, I got 0. Whenever I evaluate a sub 4, I got 0. Whenever I evaluate a sub 6, I'm going to get 0 as well. And by the time I get to a sub 7, I'm going to have 7 factorial times a7 next to a negative cosine, right? So that's going to give me that a sub 7 is going to be negative 1 over 5,040, and so on. So that's where these polynomials are coming from, right? Coming from this little trick of, first of all, assuming that I have a power series that represents sine of x, and then taking consecutive derivatives and letting x be 0 and solving for what the coefficient of my terms are going to be. All right, so we have that sine of x appears to be, in fact is, x to the first, right? And I can write that as x to the first over 1 factorial. And then the next non-zero term was negative x cubed over 3 factorial, positive x to the 5th over 5 factorial, and you get the pattern. But we didn't look at where that series converged. right? So I'd like to know what is the interval of convergence of this series, right? Now, since we've gotten an idea of how we can write down the individual terms, let's go ahead and analyze how we can write down the nth term in general. So my terms are alternating in sign. That's what this little symbol is doing right here. All of my powers are odd. That's what I'm indicating with my 2n plus 1s, right? 2n is always an even number. Add 1 to that, I get an odd. And if I start at n being 0, then I have, let's see, so this is going to be 0 plus 1, which is 1. Yep, that's the first thing I want. Whenever n is 2, this is, I'm sorry, whenever n is 1, this is 2 times 1, which is 2. Plus 1 is 3, so I have 3 factorial. I'm sorry, 3 as my power. Also 3 factorial is my denominator, and so on, right? So what I've done is analyze this a little bit to know how to represent the nth term. Now, do you remember how to find interval of convergence? Well, we begin by using the ratio test, right? And the ratio test tells us that, let's see, so it's going to use the nth term and the n plus first term. In fact, it's going to use the absolute values of those. So whenever I'm writing down the absolute value of a sub n, I'm completely ignoring the sign, right? It's not going to get involved anyway. It's going to get absorbed into the absolute value. So no reason to muck up the way the term looks here that I'm going to be working with. But I have a sub n, and then I have a sub n plus 1. How do I get in a sub n plus 1? Well, the next term is going to increase in power by 2. Of course, the denominator, the factorial of the denominator increases by 2 as well. So if I started with 2n plus 1 as my power, 2 more than that, let's see, 2n plus 1 plus 1 plus 1, that's going to be 2n plus 3. So my new power for n, the power on the n plus first term is going to be 2n plus 3. And so this is how I can write down the absolute value of my a sub n plus first term. Ratio test tells us that we need to look at the limit of the ratios of those guys. And whenever I do, so this is the n plus first term, I'm going to divide by the absolute value of the nth term. That's the same as multiplying by the reciprocal. So that's what I've done here. Do a little bit of algebraic simplification. Let's see, so absolute value of x. And notice that the only thing that's going to affect the sign of a sub n is the value of x. Right? My denominators are always positive anyway. So I'm just to simplify things, I'm keeping the absolute value sign around x. So 2n plus 3 copies of x up here, 2n plus 1 copies of x down here. Well, that's 2 more up here than I have down there. So whenever I divide, I'm just going to have 2 copies of x in my numerator. My factorials are going to behave nicely. This number right here is all the numbers between 1 and 2n plus 1 multiplied together. Well, I can think of this number as all the numbers between 1 and 2n plus 1 times, and then 2n plus 2 times 2n plus 3. So what's left, whenever I divide this term into that one to see what I have left in my denominator, 2n plus 2 times 2n plus 3 is all I'm going to be left with. So ratio test tells me that whenever this limit is less than 1, I know my series converges. Well, here's the limit. When is it less than 1? Well, this limit is equal to 0. Right? As n goes to infinity, x squared isn't changing, but my denominators are getting huge. And so that's going to make my fractions get small. So the ratio test tells me that for all the x values for which this limit is less than 1, I'm going to have a convergent series. So for all x values for which 0 is less than 1, I'm going to have a convergent series. Well, 0 is always less than 1. It doesn't matter what the x value is. And so what we've just shown is that this series converges for all values of x, every single one. So the interval of convergence is, in fact, all real numbers. The interval of convergence is everything from negative infinity to infinity. Right? So as a kind of a conclusion here, what we've just shown is that this series converges everywhere. It's fascinating, absolutely fascinating. So while we don't have a polynomial that equals sine of x, we do have a power series that equals sine of x and which equals sine of x everywhere for all values of x. Let's try it again. Let's make another wish. Let's wish this time for a power series, and again, we'll center it at 0, that's equal to cosine of x on some interval. Right, so what does that mean? So that means that we're going to, the first consequence of that wish is going to be, well, exactly what we've stated, that cosine of x is equal to a power series. This is the most generic power series we can write down. We're allowing for a constant term, we're allowing for a first degree term, a second degree term, a third degree term. Our job is to find what the coefficients are going to be. I'd like you to pause the video for just a moment and see if you can work that out. Go ahead. Pause it now. I'll be back in a moment. Okay. What did you find? Well, here's what I got. Does it agree with your work? I have that cosine of x is equal to 1 minus 1/2 x squared plus 1 over 4 factorial x to the fourth, and so on. If that's not what you got, why don't you go back and pause the video again, see if you can find any mistakes that you might have made. Now, we could shorthand this series by writing it in summation notation, right? And we're claiming that it's good on some interval. We have not decided for this function on what interval this series is going to converge, right? But we at least do know what the nth term looks like. Using that information, I'd like you to pause the video again, see if you can use the ratio test to determine what the interval of convergence is going to be. I'll wait. Go ahead, hit pause. Okay, let's see. What I got was, just like sine x, that the interval of convergence for cosine of x, this power series, turns out to be negative infinity to infinity as well. Now try wishing for a power series centered at 0 for e to the x. Right? Try wishing for that. And I want you to find the series, the power series, and the interval of convergence that results as a consequence of that wish. Go ahead. Again, I'll wait. Hit pause and come back whenever you've found a series that you believe is equal to e to the x, and after you've found the interval of convergence of your series. Okay, let's check your work. If you got that e to the x was, and isn't this beautiful, 1 plus x squared over 2 plus x cubed over 3 factorial, x to the fourth over 4 factorial, and so on, also converging everywhere on the entire real line, right? Here's how we can shorthand the notation for the series using summation notation. But to me, this is one of the most beautiful series in all of mathematics. If you got it, great. It belongs to you. Let's try one more. What happens if we wish for a power series, again, centered at 0, for the natural log function? Power series for natural log of x. Well, just like before, first consequence is, well, that we write down a generic power series and say that it's equal to log of x. What's going to happen if we play our game to find the various coefficients this time? All right, so let's try it. So again, centered at 0. So if I let x be 0, the right side collapses down to a single term, right? The right side collapses down to a sub 0. And the right side is equal to log of 0. Huh. Whoops. Log of 0 isn't defined. There is no real number that equals the log of 0. So we may wish for such a power series, but this time our wish can't be granted. It's not going to work. Can't be granted. So let's see if we can do one better. Let's try wishing for a power series for log of x centered somewhere other than 0. Well, what does that even mean? Well, what that means is that we can write log of x equal to, instead of writing down these terms that are all going to collapse whenever x is 0, let's, in place of x, write x minus something, right? I haven't indicated here yet what that might be, right? If I wanted x to be 2, for example, then I'm going to have a power series centered at 2, right? Because if all of these are 2's, then whenever x is 2, everything's going to collapse, right? The right side's going to collapse down to a sub 0. And I would be able to show that a sub 0 is equal to the natural log of 2, which is perfectly fine. But there's actually a number that's a little bit better, gives us a prettier looking series. And we're going to note that by just noting that we get a real nice number over here if x is 1, right? If x is 1, the left-hand side is exactly 0. Well, that's a prettier number than log 2, I think, whenever we're looking for an attractive power series. So let's center this at 1. Right, so let's start with a power series centered at 1. And again, I know that this is centered at 1 because if x is 1, the right-hand side collapses down to a sub 0. And I would be left with just a sub 0 equals log of 1. Log of 1 is 0. So if I have a power series centered at 1, I'm going to have that a sub 0 is equal to log of 1. A sub 0 is going to be equal to 0. Well, let's see if we can find some of these others. Derivative of natural log of x. Well, okay, that's 1 over x. And the derivative of the rest, or of the right-hand side, let's see. So this is going to be a sub 1 times the derivative of x minus 1. Well, derivative of x minus 1 is 1. Then I'm going to have, let's see, 2, so a sub 2 times the derivative of x minus 1. I'm sorry, 2a sub 2 times x minus 1 times the derivative of x minus 1, but that's 1. Then I'm going to have, let's see, 3 a sub 3 times x minus 1 squared times the derivative of x minus 1, so times 1, and so on. So whenever x is 1, the right-hand side collapses down to a 1. Right-hand side, whenever x is 1, is equal to 1. So we have a1 is equal to 1. Let's do it again. Let's take the derivative of 1 over x. Let's see. Let's write it this way so that we can think about the derivative of a little bit more easily. So the derivative is going to be negative x to the negative second. So that's going to be negative 1 over x squared. Equal to, all right, so the derivative of this side, all right, so that's going to be 2a2 times the derivative of x minus 1, which is 1. It's going to be 2 times 3, so I'm going to write as 3 factorial. A sub 3 times x minus 1 to the first times the derivative of x minus 1, which is 1. What's going to come next? I haven't, let's write this next term down here. Let's see, I would have had, this would have been what, 4a4 x minus 1 cubed. So the derivative of that's going to be 3 times 4, a sub 4, x minus 1 squared, and so on. All right, so again, this collapses to 2a2 whenever x is 1. Whenever x is 1 over here, I've got exactly negative 1. So this says negative 1 is 2a2. So a2 is going to be negative 1 over 2, negative 1 half. One more time. So let's see, this was negative x to the negative second. Whenever I take its derivative, I'm going to get 2 times, I'm sorry, yes, 2 times x to the negative third. So I'm going to get 2 over x cubed. Right over here, I'm going to have 3 factorial a3 times 1, 4 factorial a4 times x minus 1, and so on. This side's going to collapse down to 3 factorial times a3 whenever x is 1, and whenever x is 1, this is 2. So a3 is going to be, let's see, it's going to be 2 over, right, this is 2 over, and I'm looking for a3, so I'm going to divide by 3 factorial. I'm going to divide by 2 times 3. 2's are going to go away together. I'm going to wind up with 1/3. So a3 is going to be 1/3, and I think we can see what's going to happen in the next time as well. We'll just do it for good measure. So let's see, this would be what, 2, this is 2x to the negative third. If I take its derivative, I get negative 2 times 3 times x to the negative fourth. So I get let's see, negative 2 times 3 over x to the fourth. The derivative over here is going to be 4 factorial a4 plus some stuff. And so to get a sub 4, let's see. So all that, everything over here is going to go away whenever x is 1. But whenever x is 1 over here, I've got negative 2 times 3. So I'm going to get a sub 4. And a sub 4 is going to turn out to be negative 2 times 3 over 4 factorial. What's 4 factorial? That's 2 times 3 times 4. So everything's going to go away together except, let's see, the negative 1/4. And I think we can see that this pattern is going to continue. So my signs are going to alternate, and the coefficients are going to be the reciprocals of the positive integers. Right? So I think that's right. So if we started out with log x being a power series, centered at 1, what we wind up with is this series for log of x. That can be short-handed this way. And if we're looking using the ratio test to find the interval of convergence, okay, so we'll look at the a sub nth term, the a sub n plus first term. We'll divide, look at the limit. And what we get, whenever all is said and done, is that the limit of the n plus first term to the nth term in absolute value is equal to the absolute value of x minus 1. Again, the ratio test says whenever this limit is less than 1, the series converges. Well, this is the limit. So whenever this is less than 1, the series converges. So what do we have here? Well, we have a series which is centered at 1. Right? So 1 is the center of our series. This tells me, let's see, the absolute value of x minus 1 can be interpreted as the distance between the numbers x and 1. So I'm looking for x values whose distance from 1 is less than 1. Well, here's 1. The numbers whose distance from 1 is less than 1 are the numbers between 0 and 2. So whenever we found this, we actually found the radius of our series. The radius of our series was, or the radius of convergence of our series is 1. Center of our series we knew before was 1. And so we know that we can get the endpoints of our interval of convergence by adding and subtracting 1, adding and subtracting our radius of convergence from our center, to and from our center. Right? And so that tells me that the interval of convergence is either going to be the open interval from 0 to 2, the closed interval from 0 to 2, or one of the two half-open intervals between 0 and 2. We just have to check what happens at 0 and 2. Well, if we put 0 into our series up here, what we get is -1 minus a half. There's going to be -1 cubed here, so it's going to be minus a third, minus a fourth, and so on. We get a divergent series, right? This is the opposite of the harmonic series. At the other endpoint, whenever x is 2, well, whenever x is 2, x minus 1 is equal to 1. So we're going to have 1 minus a half plus a third, and so on. Well, that's an alternating harmonic series. That is the alternating harmonic series, or thought of another way, it's an alternating series for which the terms are decreasing in value and the terms are going to 0. Terms have limit 0. That's a convergent series. So, divergent whenever x is 0, so I'm not going to include that in my interval. Convergent whenever x is 2, so I am going to include that in my interval. And so the interval of my interval convergence of my series is the interval from 0 to 2. All right, so in conclusion, we've just shown that the natural log of x has a power series centered at 1 that's equal to this series right here, and that series converges on the interval from -0 to 2. In an earlier video, you may remember, let's see, we took the geometric series, which we know converges to 1 over 1 minus x. We modified it slightly by replacing all of the x's on both sides, all of the x's with negative x's. Well, if I replace this x with negative x, I'm going to have 1 over 1 plus x, right? 1 minus a negative x is 1 plus x. I'm going to have 1 over 1 plus x, and whenever I replace all of these x's with negative x's, I'll have 1 minus x. Well, negative x squared is the same as positive x squared. And then I'll have negative x cubed and so on. And then we took the integral of both sides, and after finding the constant of integration, we were able to show that the natural log of 1 plus x was equal to this series. All right. So we have two different series for log of x. Notice that this series is centered at 0, but it wasn't the natural log of x that we were finding. It was the natural log of 1 plus x. These actually agree with one another, right? Because if I took my series up here and I replaced all of my x's with 1 plus x's, so I'll replace this x with a 1 plus x. I'll replace all of these x's with a 1 plus x. Well, let's see, if I take x, replace it with 1 plus x, and then include my negative 1, this, of course, is just x. That's what I'm going to have in each of these. So I'm going to have x minus 1/2 x squared plus 1/3. Again, doing the same thing, replace my x with 1 plus x. So that's going to give me x again. So 1/3 x cubed, and so on. Right, and since I replaced all my x's with 1 plus x, that shifts the graph of my function to the left by 1 unit. So instead of converging on the open interval, half open interval from 0 to 2, shift to the left by a unit. It's going to be from -1 to 1, right? That's exactly what we had. Decided before, right? So two ways of developing series for either the natural log of x or the natural log of 1 plus x. Going to take a big jump now, but it's going to be a big jump that doesn't require much work at all, at least not much more work than what we've already done. So in general, I'd like to wish for a function that can be represented by a power series centered at something, centered at some c, maybe centered at 0, maybe centered at 1. Doesn't matter. We're just going to call the center c. Well, if I wish that, then the first consequence is going to be that f of x looks like this. This is a power series centered at c, the most general one that I could write down, right? So a sub 0, some number, plus some number times x minus c, some other number times x minus c squared, and so on. Don't know on what interval this might converge, but we're just hoping that f can be represented by some power series. So if it can, if we can write that down, then what are some consequences of that? Well, the first consequence is that, again, since function centered at c, or the series is centered at c, evaluating it at c is going to collapse me down to just a sub 0. Evaluating this side at c tells me that I'm going to get, well, evaluating this at c gives me f of c. So what I have is f of c is a sub 0. So this is f of c. If I take a derivative, I'm going to get a1, I'm going to get 2a2 times x minus c, and so on. Whenever x is c, this side collapses down to a1. Whenever x is c, this side is f prime of c. So that tells me that a1 has to be f prime of c. Let's find a2. Take another derivative. Here's the derivative I get whenever I look at the derivative of the right-hand side. Take the derivative of the left-hand side. Well, that's really easy. I'll just write down f double prime of x. Whenever x is c, this side reduces to twice a2. This side is equal to the second derivative at c. So the second derivative at c is twice a2. Well, that must mean that a2 is second derivative at c divided by 2. And so on. Right? Whenever I take the third derivative, this guy's going to bubble over. I'm going to wind up, after I evaluated c, I'm going to have 3 factorial times a3 is the third derivative at c. So divide both sides by 3 factorial, and I'm going to get a3. So this is the third derivative, evaluated at c, divided by 3 factorial. Isn't this beautiful? Look how this is working out. The pattern couldn't be any prettier. What I've got is that if f of x can be represented by a power function centered at C, this is the power function that I'm going to get. It can be abbreviated that way. And this power series is called the Taylor series expansion of our function centered at C. And that's it. That's our discussion of Taylor series, how we can build a power series for virtually any function that we can find lots of derivatives of. I find that fascinating. I hope you do too. Tune in next time, and I look forward to seeing you then. Until then, stay well. Take care.